Hello guys, and welcome to your second lesson in Unit 4. Today we're going to be talking about the relative strengths of acids and bases, so what makes one acid stronger than another acid and vice versa. And then we're going to learn how to calculate pH and other things for weak acids and bases since they behave differently than strong. So the first thing might be one of the most important concepts for you to get straight in your mind. pH is a measure of the concentration of hydronium ions. That's it. So all pH does is measure how much H3O plus is in a solution. It does not tell you about strength, okay? The reason why is I could put a ton of a weak acid into a small container and I would have an extremely low pH because it would be so concentrated, okay? So the pH, by me saying, oh, it's a pH of 1, that's a strong acid. No, it's a pH of 1. It's in a very acidic solution with a lot of hydronium. It does not mean it's strong, okay? So what does tell us if something is a weak or strong acid is the extent to which it ionizes. How product favored is it? How many of the molecules ionize? And we see this based on the Ka or the Kb value, the equilibrium constant. Okay? So it is extremely important that you understand that strength is based on the equilibrium constant. So here are some common strong acids and strong bases, okay? The strong base list looks like really long, but it's really just group 1 hydroxides and then the heavier group 2 hydroxides. Those are our strong bases. Our strong acids are perchloric acid, chloric acid, nitric acid, sulfuric acid, and then 3 of the halogens, hydrochloric, hydrobromic, and hydroiodic. You'll notice that the other main halogen that's missing there is HF. And if you remember from our POGL, we learned that HF is actually a weak acid due to its super short bond length, okay? So you need to memorize these. So a lot of times students are like, how do I know if it's a strong or a weak acid? Well, as long as you have the strong ones memorized, if it's not one of those 7, it's weak, period, the end, okay? If a base is not one of these, if it's not a group 1 or the heavier group 2 hydroxide, it's weak, period. So you just got to remember these strong ones. Okay, so let's delve a little bit more into why the equilibrium constant tells us strength of an acid or a base. So a strong acid, something like hydrochloric acid, is considered strong because it is so product favored. It has a really large K value, so that means it yields essentially 100% conjugate base and hydronium. So if you look at this depiction here, this is my original acid. Every single one of them has dissociated. So the amount of HA that I had is the exact amount of H and the exact amount of A minus that I had. That is why in the previous part, if I told you you had 0.5 molar hydrochloric acid and I asked you for the pH, you just did the negative log of 0.5. Because if the strong acid is 0.5 molar, then the concentration of H plus is 0.5 molar. But for a weak acid, it's reactant favored. They have a smaller K value, and so not all of the acid molecules dissociate. So there's not nearly as much hydronium. Most of it remains non-ionized. So whatever amount of weak acid we start with, we're going to keep most of it bound together. Only a little bit of it is going to ionize. You see that here where this is all of the bound versions. Over on the right-hand side, only one dissociated. So that's what makes it a weak acid. We have the exact same concept for a strong and a weak base. so strong, are going to be very product favored. They have large K values. They pretty much 100% dissociate. That's why oftentimes I mentioned it in that first worksheet that we did, that for strong, we're going to see a single-sided arrow. We basically go to completion, but for weak, we're going to see an equilibrium. And that's because weak bases can go both ways. They're mostly reactant favored. They have small K values. Most of them remain undissociated or unionized. And as long as they're undissociated, they're not actually producing hydroxide or hydronium. So as we know, K, the equilibrium constant, is what tells us the extent of a reaction. It is what tells us how reactant favored or how product favored something is. So K is just a generic equilibrium expression. Ka is specifically for an acid. And then Kb is specifically for a base. So as we know, the bigger the Ka, the stronger the acid. The bigger the Kb, the stronger the base. Weaker is smaller K values. All right, so let's look at the relationship between Ka and Kb. Because if I have Ka for an acid, then the Kb would be for its conjugate base. And if I have Kb for a base, then the Ka for its conjugate acid. So let's look at this first example. I have hydrocyanic acid and then the cyanide ion. I'm told the Ka for the acid is 4 times 10 to the negative 10, and then for the cyanide ion, it's 2.5 times 10 to the negative 5. So the cyanide ion is a stronger base than the hydrocyanic acid is an acid. So if I multiply these two together, I get 1 times 10 to the negative 14. And I bet you can guess, if I do 7.2 times 10 to the negative 4, which is the Ka of HF, times 1.4, 10 to the negative 11, I get 1 times 10 to the negative 14. So Ka times Kb will always equal Kw. That is given to you right here on your equation sheet. So already we had seen that Kw equals the concentration of H plus times OH minus, and it's 1 times 10 to the negative 14. It also equals Ka times Kb. Now, why does it equal Ka times Kb? Well, I'm glad you asked. If you look at this first equation, it's the acid dissociation for hydrofluoric acid. That would have a value of Ka. Well, its complement reaction for its conjugate base would be the fluorine ion plus water with HF and OH minus, and that would be Kb. So remember last unit when we learned that when you add reactions together, you multiply the K values. So if we add these together, canceling things that appear on both sides, we're left with water plus water yields hydronium and hydroxide. That is the auto-ionization of water, which has a K value of Kw. So Ka times Kb equals Kw. So look at this example. What is the ionization constant for the weak acid CH32 NH2+, the conjugate acid of the weak base CH32 NH, and it gives me the Kb. Well, as long as I know the Kb, I can always find Ka for the conjugate, because Ka times Kb is Kw. Kw is 1 times 10 to the negative 14. Tells me that equals Ka times 7.4 times 10 to the negative 4. So when I divide 1 times 10 to the negative 14 by 7 times 10 to the negative 4, I get 1.35 times 10 to the negative 11. So the Ka of that conjugate acid is 1.35 times 10 to the negative 11. So something you should notice is if every time I multiply them together times KB, it always equals 1 times 10 to the negative 14. It's a constant, 1 times 10 to the negative 14, as long as we're at 25 degrees. So as one value goes up, the other must come down. Because when I multiply them together, they have to equal 1 times 10 to the negative 14. So the bigger my Ka, the lower my Kb. The bigger my Kb, the lower my Ka. So what that means is that the stronger the acid, the weaker its conjugate base is. The stronger the base, the weaker its conjugate acid is. So we can kind of see this depicted here. So on the left-hand side, we see acids with the strongest at the top. And on the right-hand side, we see bases with the strongest at the bottom. On the, they're listed with their conjugate pair. So in this top left-hand corner are our strongest acids. Their conjugate base is weaker than water, meaning the conjugate of that strong acid has no basic character whatsoever. So with water, it would just be neutral because the acids are so strong. Now, if we look at the opposite side, our strongest bases down here, they are so strong that their conjugate acid is weaker than water. So if their conjugate acid is with water, they're going to make, it's just going to be neutral. They don't have any acidic character. Now, where it gets tricky is in the middle. So in the middle, the acids and the bases are both considered weak. Neither of them are in our strong category. And so the conjugate of an acid in the middle, that conjugate base can act as a base. And the conjugate acid of a base in this area can act as an acid. So there is acidic character to these acids, and then there is acidic character to those bases in the middle. And we'll talk a lot more about this when we get to the last part of this unit, which is salt hydrolysis. So if we look for Ka or Kb values, we're looking at strong acids and strong bases. Essentially, they 100% ionize. So it's actually very difficult to differentiate and give them different K values. So we just consider them to be 100% one-sided, not even in an equilibrium. Now, if we want to talk about the relative strength of binary compounds, so how they compare to one another. So binary meaning they're made up of two things. So the molecular structure affects its strength. And this is, I want you to think back to the POGIL, okay? So as we go up and down a group, it is the strength of the bond that is affecting the structure that's then affecting the strength. So as we go down a group, an acid is actually going to get stronger because the bond strength decreases. Across a period, from left to right, the acid strength is going to increase because of the increase in electronegativity and polarity. So this is just a trend to understand and to remember. And your POGIL went way in more depth than I need to go right now because you already did it. Oxyacids were also covered in your POGIL. So this is when the acidic proton is attached to an oxygen. The more oxygens there are, the stronger the acid is going to be because the oxygens pull everything away, making that hydrogen easier to be removed. Acid strength also increases as the electronegativity of that central atom increases for the same reason. It pulls the electrons towards it, easier for that hydrogen to be removed. If you're a little bit like, what? Go back to your POGIL and look through all of that. Okay, so kind of the last thing for this lesson. Since weak acids and bases do not 100% ionize, their pH calculations are not as simple as plugging the concentration I'm given into the negative log formula. Because, as we saw in that image back where we looked at the difference between a strong acid and a strong base, because they don't fully ionize, whatever my initial concentration of isn't my concentration of my products because they're in equilibrium. And so when we have weak acids or weak bases that have K values between -2, -14, they could get way even smaller than -14. We have to set up an equilibrium, okay? So for example, the pH of a 0.0516 molar solution of nitrous acid is 2.34. What is its Ka? So here, I'm actually not even asked to calculate pH. I'm given pH, and I'm asked to calculate the K value. This is just like last unit when you were given the initial concentration and one of the equilibrium concentrations, and I'll show you how. So because we know the pH, we can determine the concentration of H3O+, because we know that if we take 10 to the negative pH, that will tell me the concentration of H3O+ at equilibrium. So in this problem then, I am given the initial concentration of the reactant, and I am given indirectly by doing this calculation the concentration of one of the products at equilibrium. So we're going to set up an ice chart. So if you look here, we have so our ice chart, the initial concentration I was given of the acid was 0.0516. I was given that in the problem. I don't have any products at the moment. Minus X. Now this would be plus X and plus X. What I typically do, and you'll see in the rest of the problems, I just mark through water so I don't forget and accidentally fill things in for it, because water is a pure liquid and it does not appear in equilibrium expressions. We can't change its concentration. Okay? So then when I know the pH, I take 10 to the negative pH and I get 0.0046. Well, if my pH is 2.34, then my concentration of hydronium is 0.0046. So I fill that in here. Well, if 0 plus X equals 0.0046, then X equals 0.0046. So then this is 0.0046, and then here I do 0.015 minus X is 0.0470. Now, with our weak acid and weak base problems, we have really small K values. So we get to ignore X. So instead of plugging in 0.0516, well, actually, I take all that back. I don't know why I have that put there, because in this one, we don't even have to worry about ignoring X because we know X. So yeah, just ignore that. All right, in this example, we don't have to ignore X because we know X. We're going to plug in our equilibrium concentrations into my expression, and that's going to give me my K value. Okay? Okay, so here's another example. What is the concentration of hydronium ions and the pH in a 0.534 molar solution of formic acid? And I'm given the Ka value. So this is a problem like last unit when I was given the initial concentration and I was given the K value and I had to find the equilibrium concentrations, because this right here is the concentration of hydronium ions, and then because the negative log of the concentration of hydronium equals pH, once I know this value, I will know the pH. Okay? So I have my ice chart with my equation. My initial concentration of acid is 0.534. I don't have any product to start with. I'm just going to mark through water, minus X, plus X, plus X. So here I get 0.534 minus X, X, and X. All right. Well, Ka is going to equal hydronium times ion formate over the concentration of formic acid. So now I'm going to plug in 1.8 times 10 to the negative 4, which is the Ka value that I was given, equals x times x over, here's where I kind of jumped the gun last slide. Here is where, because K is small, I can ignore the change, I can ignore minus x, and so this is just over 0.534. So then when I multiply 0.534 times 1.8 times 10 to the negative 4, I get, oh, I have that part written down, sorry. 9.61 times 10 to the negative 5 equals x squared. So I got to square root both sides. And x equals 0.0098. So that right there is my concentration of hydronium. That was the first part of my question. So then I'm going to take the negative log of that to get my pH, which is 2.01. There's my two answers. All right, this asks me find the concentration of the hydroxide ion in a 0.25 molar solution of trimethylamine, a weak base. Also find the pH. The only difference in this problem and the last problem is we're working with a base now. So we're creating hydroxide, and then we're given Kb. I'm asked to find the pH. So what I'm going to have to do is figure out the concentration of hydroxide, which is going to give me POH, and then do 14 minus to get pH. So I just have to do an extra step. All right, so I'm starting with 0.25 molar, 0 and 0. So then I have minus x plus x plus x. 0.25 minus x, x and x. Oops. Kb is equal to products over reactant. And then this is so small, 7.4 times 10 to the negative 5, that I can ignore the x. So I get x squared over 0.25 because it's x times x on the top. So then when I multiply 7.4 times 10 to the negative 5 by 0.25, I get 1.85 times 10 to the negative 5 equals x squared. So then I'm going to take the square root. I get 0.0043 molar. So that is equal to the concentration of hydroxide, which is the first part of my question. So then I'm going to take the negative log of that. And I get 2.37. Now, some of you are going to be tempted to stop there, but remember that's POH. It should also clue you in that you're not done because this is a base, so we should not have an acidic pH. So we have to do 14 minus 2.37, and we get 11.63 is the pH. All right, next one, determine the Ka for hydrogen sulfate in a 0.1 molar solution if the acid is 29% ionized. So here I went ahead and wrote out the equation. I knew how to do that because this is an acid, so it's going to donate its hydrogen to water, leaving behind the conjugate base and hydronium. So I'm starting with 0.1 molar, 0 and 0. I'm going to mark through my water, minus x plus x plus X. So now this tells me that the acid is 29% ionized. So I've got to figure out what is 29% of 0.1. So I'm going to do 0.1 molar times 0.29, so that equals 0.029. So if it is 29% ionized, then X is equal to 0.029, because that is 29% of 0.1, so that's 29% ionized. So now I can plug in 0.1 minus 0.029. Whoops. And I get 0.071. And so now to calculate K, I've got 0.029 times 0.029 divided by 0.071. So Ka equals 1.2 times 10 to the negative 2. So there is my K value, starting with the initial, and then I was told the percent ionization, which is another way of telling me one of the equilibrium concentrations. All right, last question. This time it is a base. Determine the Kb for the nitrate ion. So if I know it's a base, then it's going to take a hydrogen from water, becoming HNO2, the conjugate acid, and hydroxide. So I'm starting with a 0.1 molar solution. This time it's only 0.0015% ionized. So very little ionization. So what I should expect, 0.0015% ionization compared to the previous slide where it was 29%. This is a much weaker and should have a much lower K value. So to figure out my X, I've got to do 0.1 molar times. Now remember, when we find a percent of something, we multiply by, or we divide by 100. Sorry. So even though this is already already a decimal, we do still have to turn it into a percent. So that means that my concentration, 1.5 times 10 to the negative 6. So that's my X value. Oops. Now, technically, I could do 0.1 minus 1.5 times 10 to the negative 6, because I know that that's my X value. But I get 0.099985. So that's going to essentially round to 0.1. 10 to the negative 6 times 1.5 times 10 to the negative 6 over 0.1. And I get that Kb is 2.25 10 to the negative 11. So like we guessed, based on how little of it ionized, we have a much smaller K value than I had in the previous one. This right here also explains to you why, when we have really small K values, this change in X is insignificant because it ends up rounding to the same thing. That's why the ignore X rule is there. All right, so we're going to do lots more practice. I kept it under 30 minutes. So if you're listening, you can send me a text on Remind that says, "Way to go, Miss Wilkins." All right, guys, I will see you guys soon.